Hi, my name is Kurt Talka. I'm at the University of California, San Diego, and I'd like to show you what I've done with the Beagle Bone Blue, Simulink, and the EDUMiP. Our lab focuses on dynamic systems and controls. For this project, we're focusing on the EDUMiP seen here, a mobile inverted pendulum. Leveraging the extensive C library developed by James Strawson to interface with the Beagle Bone Blue, shown here, I worked directly with MathWorks to develop a Simulink coder support package for Beagle Bone Blue. All the low-level drivers for touching the hardware are wrapped so that there are individual blocks for all the low-level components, such as get encoder readings and driving motors. The hardware plant is shown here, specifically the transfer function of a cascaded system with G1 outputting the body angle theta determined using a complementary filter from the IMU, and G2 outputting the wheel angle determined from a combination of measurements from each wheel encoder. The input into the plant is the commanded motor speed, shown in blue on the left. The top-level simulation model is shown here. It is split up into three systems. The logic level, which handles the startup logic and all the balancing controller, the monitor, which monitors the pause button on the Beagle Bone Blue, as well as flashes a green LED, and the dashboard. From the dashboard, the end user can select one of 4 pre-specified controllers operating at different frequency rates, or they can input their own developed controller. Shown here is the balance subsystem. This system consists of a controller, a saturation block, as well as the hardware plant already discussed. The controller consists of 2 discrete time controllers, shown here denoted as the slow loop and fast loop controllers in a cascaded system. These 2 blocks are a case structure linked to the dashboard where the end user can select which controller to use, shown on the bottom left. The case structure shown here has 5 simple controllers, each with a discrete time controller and its own gain. Here's an example of the 50 Hz rate controller. Additionally, the last one allows the end user to specify their own gains for their own developed controller. Additionally, they have the ability to select the frequency rate of that controller. Lastly, in the balance system is the control saturation and scaling. In this block, we're saturating the motor input U between -1 and 1. Additionally, we're implementing a soft start, which ramps the motor input U from 0 to 100% over about 1 second. Next, let's look at the startup logic. The startup logic has 3 flags: a saturation flag, an upright flag, and a wait to start flag. All 3 of these flags feed into an enable flag, which triggers the control loop when true. The saturation detection counter counts anytime the motor input U is outside the saturation limits. Whenever that counter is less than the saturation timeout, the timeout flag is true. Similarly, the upright flag gets triggered anytime the robot is vertical for longer than 1 second. Lastly, the IMU and complementary filter take approximately 3 seconds to stabilize. Therefore, a startup flag waits 3 seconds before becoming true. Additionally, as already mentioned, a soft start counter increases the motor input U from 0 to 100% over 0.9 seconds. Let's watch the system in action. Here we have a 100 Hz loop controller shown. In the top right, we have the motor input U, the saturated and scaled outputs. In the bottom left, we have theta, the attitude of the body. In the bottom right, we have phi, the wheel angle. As you can see, the robot is relatively robust. Thank you for watching my Simulink and EDUMiP videos. Please see my GitHub page for more information.